Hi, this is Schwartz from MasterMathMentor.com. This is video BC07b. The topic is fluid force, and it covers the BC manual, pages 168 through 170. We define pressure as the force per unit of area over the surface of a body. We see to the right we have a column of water that is 5 feet in height, but only 1 inch square. This column of water weighs 2.15 pounds. So the fluid pressure at a depth of 5 feet is 2.15 pounds per square inch. At 10 feet, this would increase to 4.3 pounds per square inch, as the pressure is proportional to the depth of the object in the fluid. So at a mile down, the fluid force is over a ton per square inch. To find the fluid pressure of an object at depth h in a liquid, we use the formula pressure is equal to, we'll use the variable p, WH, where W is the weight density of the liquid per unit of volume. Here are some common fluids and their weight density measured in pounds per cubic foot. Gasoline is 46 pounds per cubic foot, alcohol 49.3, kerosene 51.2, turpentine 54.2, and regular water 62.4. Beer is close to water, 63. Seawater is slightly heavier at 64, as is milk. A sugar solution has a weight density of 87.2 pounds per cubic foot, and mercury has a whopping weight density of 849 pounds per cubic foot. When calculating fluid pressure, we use a physical law called Pascal's principle, named after the French mathematician Blaise Pascal, 1623 to 1662. This law states that the pressure exerted by a fluid at a depth h is transmitted equally in all directions. We see this if we punch a hole in the side of a plastic water bottle. Even though the pressure is created by the weight of the water vertically from the top of the bottle, the water spurting out horizontally from the bottle is due to Pascal's principle. We know that fluid pressure is measured in force per unit area. We now define fluid force as a force on a submerged horizontal surface of area A, and its formula is given by F is equal to PA, which is equal to the fluid pressure times the area. For problem 1, we see a rectangular piece of glass measuring 2 feet by 3 feet lying on the bottom of a 5-foot deep swimming pool. We would like to find the fluid force on the glass. We know that the weight density of water is 62.4 pounds per cubic foot. Since the glass is submerged in 5 feet of water, then our fluid pressure P is equal to WH, which is equal to 62.4 pounds per cubic foot times 5 feet. And this gives us 312 pounds per square feet. We don't normally show our units in calculations like this, but I think it's important to show them to show where the cancellation occurs. Since the total area of the glass is 6 square feet, then our fluid force, F, is equal to PA, which is 312 pounds per square foot times 6 square feet. The square feet cancel, and we are left with 1,872 pounds of fluid force on the glass. The size of the surrounding water is irrelevant to the problem. This glass could be in a pool, a bathtub, a lake, or an ocean. This problem is just simple math because the glass is lying flat on the bottom of the pool. We don't need calculus. But if a surface is submerged vertically in a fluid, the problem becomes more complex because the depth is no longer constant, and therefore the pressure is not constant as well. Remember that because of Pascal's principle, the pressure at a depth is transmitted in all directions. Remember the bottle with the water leaking out from the sides. So in an aquarium, for example, the pressure of the water at the bottom of the tank pressing against the sides of the aquarium is greater than the pressure of the water pressing against the sides at the top of the aquarium. As shown in the picture, we have a submerged vertical plate in a liquid, and we'd like to find the fluid force against that plate. We draw a series of rectangles, and we show one of them, of length L of y sub I and height delta y at a distance h of y sub I from the surface of the liquid. So the fluid force of a representative rectangle is delta F sub I is the weight density times the depth times the area, which is W times H sub Y sub I times L sub Y sub I delta Y. And if we sum all of these rectangles, we get the fluid force F is equal to the limit as delta Y approaches 0 of W times summation I equals 1 to infinity of H Y sub I times L of Y sub I times delta Y. We know the summation represents an integral, so we can say that the force exerted by a fluid of constant weight density against a submerged vertical plate region from y equals c to y equals d is given by F equals W integral from c to d of h of y, L of y, dy, where h of y is the depth of the fluid at a point xy and L of y is equal to the horizontal length of the region at the point xy. Let's show a series of examples how to use this formula. Number 2 reads, a vertical gate in a dam is 10 feet long by 4 feet high. We want to find the fluid force on the gate when the top of it is 6 feet below water level. We see the picture on the left that describes the situation. To do this, we draw a representative rectangle somewhere on our gate. And now we have to label points as we did with word problems. We can either place the gate below the x-axis, which seems to make the most sense, or above the x-axis. So if we label the points below the x-axis, then the x-axis is the point on the left-hand side in red, -5, 0, and the bottom is -5, -10. The gate top is at the point -5, -6, and a representative place for the gate rectangle is -5y. If we place the origin at the bottom, we use the blue points on the right side, and our bottom will be 5, 0, while the very top will be 5, 10. The top of the gate is 5, 4, and the representative rectangle is at the point 5y. It should be clear that no matter where we place the x-axis, the length of the gate is always 10 because it is a rectangle. Our formula for fluid force involves the depth of our representative rectangle. This is always the y-coordinate of water level minus the y-coordinate of our rectangle. So if the gate is below the x-axis, our depth is 0 minus y, which is negative y. And if our gate is above the x-axis, our depth is simply 10 minus y. So we are now ready for our fluid force against the gate. If we put our gate below the x-axis, then our fluid force is our weight density, 62.4, times the integral of our length, 10, times our depth, negative y, dy. And y will run from the gate limits, negative 10 to negative 6. We end up getting 19,968 pounds. If our gate is above the x-axis, then the fluid force will simply be, again, 62.4 of our length, 10, times our depth, 10 minus y, and now we will run our limits from 0 to 4. We get the same answer, 19,968 pounds. Even though the doing it below has more negative signs in it, I prefer that method because it seems to describe the situation the best, that the gate is below the water level, which will be the x-axis. Now, what happens to our fluid force against the gate if the gate is moved to water level? The formula is exactly as it was before, except we change the limits of integration. If the gate is below the x-axis, we integrate from negative 4 to 0. If it's above the x-axis, we integrate from 6 to 10. In both cases, we get 4,992 pounds. And that is considerably less than the almost 20,000 pounds we had before, because the gate is not nearly as deep, and therefore there's not as much force against it. If the top of the gate is twice as deep as originally stated, our below formula only changes the limits of integration. 62.4 integral from negative 16 to negative 12 of negative 10y dy. If we use the gate above the x-axis, then the depth changes, but the limits of integration stay the same. 62.4 integral from 0 to 4 of 10, 16 minus y dy. In both cases, we get 34,944 pounds. If we compare the 34,944 to the 19,968 pounds, we get 1.75, meaning that there is 75% greater fluid force on the gate by doubling the depth. Number 3 is similar. We still have a vertical gate in a dam, but now it is trapezoidal shaped, 10 feet across the top, 6 feet across the bottom, and 4 feet high. We again want to find the fluid force on the gate when the top of it is 6 feet below water level. We again set up points based upon where we place the x-axis. If the gate is below the x-axis, then the top of the water is the point negative 5, 0. The top of the gate is negative 5, negative 6. The bottom of the gate is negative 3, negative 10. And a representative rectangle is the point xy. If we make the gate above the x-axis, then the bottom of the gate is the point 30, the top of the gate is the point 54, the top of the water level is 510, and the representative point on the rectangle will be xy. As before, we need the depth of our representative rectangle. If the gate is below the x-axis, we use the formula 0 minus y, which is negative y. If the gate is above the x-axis, then the depth is 10 minus y. It's the same as we did on the previous problem. In the previous problem, the length of our gate was a constant because the shape was a rectangle. But now it is no longer a constant as the shape is a trapezoid. However, we can say that the length of our gate is either equal to negative 2x or positive 2x. We use negative 2x if we use our red points where the gate is below the x-axis, and we use the blue points if our gate is above the x-axis. In either case, we need the equation of the lines connecting the points. So if we use the red points, we want the line connecting negative 5, negative 6, and negative 3, negative 10. Our slope is negative 2, and therefore our equation is y plus 10 is equal to negative 2x plus 3. That gives y equals negative 2x minus 16, and negative 2x is equal to y plus 16. If we use the points when the gate is above the x-axis, then the slope is, joining the points 5, 4, and 3, 0, the slope is 2. Our equation is y is equal to 2 quantity x minus 3, and solving for 2x, we get 2x equals y plus 6. So now we need to calculate the fluid force against the gate. And our formula, if we are having the gate below the x-axis, then it is 62.4. The integral of y plus 16 times negative y dy, and y will run from negative 10 to negative 6, and we get 15,641.6 pounds. If the gate is above the x-axis, then our fluid force is 62.4. The integral of y plus 6 times 10 minus y dy, and now y runs from 0 to 4. We get the same answer, 15,641.6 pounds. Finally, when you do problems like this, you need to determine the placement of the gate relative to the x-axis. You don't have to do them both ways as we have done in the problems. However, if you are not sure, it is a good idea to do them both ways and make sure that your answers match. Problem number 4 reads, Atlantis Adventures gives tourists a chance to experience traveling on a mini-sub to see underwater sea creatures. It has 2-foot diameter circular windows, and it goes down to a depth of 100 feet. We'd like to calculate the fluid force against the windows at that depth. To do this, again, we place important points on the diagram and choose one of them for the origin. In this case, there is one obvious choice that will make our calculations easier. Placing the origin at the center of the circle will be the best choice, as the equation of a circle is easiest if the center is at the point 0, 0. X squared plus y squared equals r squared. We also show the other important points on the circle from the top clockwise, 0, 1, 1, 0, 0, negative 1, negative 1, 0. The top of the water, therefore, is the point 0, 100. We draw a representative rectangle showing the coordinate xy. First, we need the depth of our representative rectangle, and as before, it's top minus bottom, so it will simply be 100 minus y. Next, we need an expression to represent the length of our representative rectangle, and we know that is 2x. The relationship between x and y is x squared plus y squared is equal to 1, and x squared is equal to 1 minus y squared. So therefore x is equal to the square root of 1 minus y squared, and since we want 2x, that will be 2 square root of 1 minus y squared. So the fluid force against our window is 62.4 times 2 square root of 1 minus y squared times 100 minus y dy, and we will integrate this from the location of the window in terms of y from -1 to 1. We end up getting 19,603.538 pounds, which is approximately 9.8 tons. People whose cars fall into a lake or river frequently die before they can get out. It doesn't take much depth for the fluid force against the door making it impossible to open. And as we see, the fluid force against the window could make it impossible to open as well. Contrary to thought, it's not the water stopping the power windows from operating. It's simply the force against the window that would make even a hand crank window impossible to open, even in just several feet of water. If we double the size of the window's diameter, we find that the fluid force gets much larger. Our equation now is fluid force is 62.4. Our integral now runs from -2 to 2 of 2 square root of 4 minus y squared 100 minus y dy. And this gives 78,414.153 pounds, or approximately 39.2 tons. On submersibles that explore the depths of the ocean, the windows are made of special thick acrylic that are only about 7 inches in diameter. And when exploring wrecks like the Titanic, which is approximately 2 miles down, they can experience forces of over 600 tons.